Hey everyone, welcome to this explainer. I'm so thrilled to have you here today because we're going to look at something that literally feels like pure magic, but is actually the fundamental chemistry keeping our modern world spinning. We're talking about manipulating invisible chemical forces to run massive global industries, feed billions of people, and power our daily lives. Let's get right into it.
Let me ask you a question right off the bat. Are all chemical reactions permanent, one-way streets? I mean, think about it. When you burn a piece of wood or bake a cake, you can't exactly unburn the ash or unbake the flour, right? We kind of carry this misconception that once a chemical reaction happens, it's done. It can never be undone. But what if I told you that in the chemical world, some streets have traffic flowing in both directions at the exact same time?
Here's our roadmap for today's explainer. First, what are reversible reactions? Second, achieving dynamic equilibrium. Third, Le Chatelet's principle. Fourth, the Haber process. And finally, number 5, the contact process.
All right, Section 1. What exactly are reversible reactions?
A reversible reaction is, well, exactly what it sounds like. It's a chemical reaction where the products can actually react with each other to just reform the original reactants. On paper, chemists show this using a very specific symbol, a double half arrow. You've got the top arrow pointing right for the forward reaction and the bottom arrow pointing left for the backward reaction. It just tells us the whole thing can go both ways. A perfect real-world example of this is heating and hydrating cobalt-2 chloride. You start with these beautiful pink hydrated crystals. If you add heat, which is an endothermic process, you drive the forward reaction. That evaporates the water and leaves behind completely dry or anhydrous blue crystals. But here's the real magic. If you take away the heat and add just a few drops of water back to those blue crystals, it drives the backward reaction. They turn pink again, releasing the heat they absorbed earlier in a completely exothermic reaction. It's totally reversible.
Moving on to Section 2. Achieving dynamic equilibrium. So, what actually happens when we mix these chemicals together, step back, and just let these two-way reactions run their natural course? Well, before a reaction can ever reach equilibrium, we have to establish the environment it lives in. We basically have two options. There's an open system, where substances and gases can just enter or escape into the air. Or there's a closed system, a completely sealed environment where absolutely nothing gets in or out. And this is absolutely crucial. A state of equilibrium can never, ever happen if your products keep escaping out into the room.
Just think about iodine vapor in a test tube. If the tube is open, that purple vapor just drifts away into the air. The backward reaction literally can't happen because, well, the vapor is gone. But if you seal that tube, the vapor gets trapped. The solid iodine turns into gas, and the gas turns back into solid. Because nothing escapes, this closed system is the strict, absolute prerequisite for equilibrium.
And when you leave that closed system alone for a bit, we eventually hit what's called dynamic equilibrium. This is the exact moment when the forward reaction and the backward reaction are happening at the completely equal exact same rate. Because they're moving at the exact same speed, the overall concentrations of your reactants and products, they just stop changing. Now, dynamic is the key word here, right? The reaction hasn't stopped. Molecules are still breaking down and reforming frantically, but since they're doing it at the same speed, there's no overall visible change. It's kind of like walking up a down escalator at the exact same speed the stairs are moving. You're putting in a lot of work, but you're not actually going anywhere.
If you map this out on a graph, it becomes super clear. When we start, we only have reactants, so the forward rate is super fast, but it naturally slows down as those reactants get used up. Now, the reverse reaction starts at 0, because we don't have any products yet. But as products form, that reverse rate speeds up. Eventually, those two reaction rates converge. That exact point where the rates merge horizontally, that is the exact moment dynamic equilibrium is achieved. Both rates are perfectly matched.
Section 3. Le Chatelet's principle.
Now, if you're an industrial chemist, you don't just want a perfectly balanced reaction. You want to make a product, and you want to make a massive amount of it. To hack that balance, we use Le Chatelet's principle. Discovered by a French engineer in the 19th century, this is essentially the rule book of chemistry. The principle states that if you change the conditions of a system at equilibrium, the system will automatically shift to oppose that change. It's like a cheat sheet. Increase the temperature, the system tries to cool itself down by moving in the endothermic direction to absorb that extra heat. Increase the pressure, it tries to relieve that squeeze by shifting toward the side of the equation with fewer gas molecules. Basically, by intentionally stressing a reaction, we can actually force the equilibrium to shift and produce way more of the specific chemicals we want.
Let's look at how this applies in Section 4. the Haber process.
Let's scale this up to real-world macro manufacturing. The Haber process is this massive industrial method used to make ammonia, which is absolutely critical for creating the fertilizers that literally feed billions of people globally. Producing ammonia is a reversible reaction that combines nitrogen and hydrogen gas. On an industrial scale, it happens in 5 clear steps. 1, we pump the raw gases in. 2, we compress them to a crushing 200 atmospheres of pressure. 3, we heat them to 450 degrees Celsius over beds of catalytic iron. 4, as the ammonia forms, it's immediately cooled, liquefied, and removed so it can't run the backward reaction. And 5, all those unreacted gases are recycled right back to the start. It is a continuous, closed-system loop.
But here's where it gets super fascinating. The Haber process isn't just pure chemistry. It's honestly a high-stakes business negotiation. We call it the Great Compromise. See, according to Le Chatelier, because making ammonia releases heat, we should theoretically run this reaction ice-cold to get the absolute maximum yield. But if we actually did that, the reaction would take years. So we compromise. We run it at 450 degrees Celsius, sacrificing maximum yield for a reaction rate that makes actual business sense. We also compromise on pressure. 200 atmospheres is high, sure, but higher would yield way more ammonia. The catch? Extreme pressure needs incredibly expensive, dangerous equipment that could literally explode. Oh, and finally, we throw in an iron catalyst. It doesn't actually change the equilibrium, but it speeds up how fast we reach it, which lets us use that lower 450-degree temperature and save an absolute fortune on energy costs.
And that brings us to Section 5, the contact process.
You know sulfuric acid, it's an essential ingredient for everything from your car battery to the laundry detergent you use every week. The core reversible reaction happening in the contact process is the oxidation of sulfur dioxide, literally adding oxygen straight from the air to create sulfur trioxide. And just like the Haber process, we use a catalyst to speed things up. But for this one, we use vanadium 5 oxide.
And just like the Haber process, the contact process relies on some really brilliant compromises. We use that same 450-degree temperature to balance out a decent yield with a reaction speed that keeps the factory moving. But take a look at the pressure. We only use 2 atmospheres. That is barely above normal room pressure. Why? Well, because the natural equilibrium of this specific reaction already heavily favors the product side. Even at low pressure, you're getting a 96% yield of sulfur trioxide. Spending millions of dollars on extreme pressure equipment just to squeeze out an extra 2 or 3%, it simply isn't worth the financial cost, or the risk of explosions, or the risk of accidentally liquefying the sulfur dioxide.
It is truly amazing when you step back and look at the big picture. By simply understanding that chemistry isn't a one-way street, and by mastering the rules of dynamic equilibrium and Le Chatelier's principle, we've figured out how to feed the world and build massive global industries. We've literally learned how to negotiate with nature itself, constantly balancing yield, time, and safety. So I'll leave you with this provocative thought. If manipulating these invisible chemical balances has already shaped the modern world this deeply, what other invisible balances are out there, just waiting for us to manipulate next? Thanks for listening, and I'll see you next time on The Explainer.